About. Please give a round of applause to Terence Lee.
Hello. Okay, this is my working. So, like you're saying, I'm Terence. I go by Hone02 on Twitter. I come from Austin, Texas. Like Richard, we have amazing tacos. If you are ever coming through in town, tweet at me and I'd be more than happy to take you out to some delicious tacos if I'm actually in town. We also are probably more famously known for Awesome Barbecue, Franklin Barbecue. You can get some pretty awesome meat. We do really good brisket. Phil can tell you all about it.
Yep.
I also am known for wearing blue hats. I brought some blue hat stickers, so if anyone actually wants a sticker, I have a bunch here. And I also brought some Bundler stickers, so if you like the Bundler project, I also have stickers for that. I work at Heroku, like Richard was saying. I want to thank Heroku a lot for giving both Richard and I the time to work on a bunch of open source stuff in the Ruby community, and sending this out here around the world to speak at various conferences. So thank you, Heroku, and also sponsoring Matt's Koichi and Noko. So a lot of the stuff I'm going to be talking about in this talk is actually stuff that Heroku had some financial burden paying for. I also work with this great guy who has really awesome photos. I get to take a lot of good photos of that. And then finally, Zizak was supposed to be here with us, but he couldn't make it, so I wanted to give a shout out to him for not being here, I guess. So I'm here to talk about tooling in Ruby. So I think Richard did a pretty awesome job talking about science and measuring and performance, but I'm not going to be talking about benchmarking per se. So I did some Java stuff back in the day, and I'm super jealous of, I guess, the JRuby guys and kind of the Java tooling. So this is Visual VM. And you can see it when you're doing profiling and other things, it has some pretty awesome graphs of just like introspection into your app, of like what you can see your app is doing, like CPU usage, memory, and it's highly interactive, and you can dump your memory states out and then load it up in another Java process. It's like pretty awesome stuff. And so I was looking in what we have in the Ruby space, and over the last few years, the core team has done a bunch of work in adding hooks and kind of getting us tools to be able to look into some more of these things. So for this talk today, I'm going to be covering trace points, object space, and the allocation tracer gem, which Koichi wrote. I think when I gave this talk at Ruby on Rails, Akira Matsuda joked and was like, "This is the Koichi talk," because I think Koichi worked on a lot of this stuff. So to talk about trace points, we have to first look at set trace func, which has been around for a while, and it's method off of kernel. And basically, you set this. It's just a method call, and then you pass it a prop, and you can basically have it call out, and it gets run for a bunch of events throughout your Ruby code. So here's an example of enabling this this trace, and then we want to print out the following things: the actual event that is being called that's causing this to be run, what file it's coming from, the line number in the file, the class or the method. The ID is the method name, and then class is the class name. So if we have a really sample example code here, so we're instantiating this class foo, it has a single method that returns Baz, and then we're calling it. So when we run this code, it'll go through and trace this, and then at the end here, we're going to, if you pass nil in, it will disable the trace from running anymore, and then so when we call foo.new, below it, you won't see any more tracing information. So when you run that code on the previous slide, you get this output. So the first thing you see is that it actually traces itself. So when you call set trace func, you see that first line there. And you see it's it has the cterm return event on the left, and then you see the file that it's in and what line it was on, and then the method and then the class. So as we walk through this thing, you see that corresponds to that thing at the top. And then as we're instantiating that class, we see that is also being traced. So you're seeing all the output from that there and where that's being called from in the various events. And then you see that we're also defining this method, and that gets added. And then that whole thing encapsulates the whole class being defined. And then when we call new from food new, we see that from there. And then as we actually execute the method, we also see another trace there. So as you can see, like all this stuff allows you to get a lot more introspection of all the events happening in even this very simple piece of code here. So these are all the events that it actually will get called upon. So you saw call from before, and call stands for any C function that gets called, and then you get the return, another event gets raised. Call and return corresponds to normal Ruby methods. So a Ruby method call, Ruby method return, like that set trace func that you define will get called. Anytime you define a new class or it gets finished, will get an event, as well as every single line on there will get a function call. And then anytime you raise an event, so any exception that you're raising will also get a set trace func. So you can imagine instrumenting your code base to try to dig more into what your code is actually doing. But at the same time, it's probably pretty expensive if that prop call is kind of expensive, because if you're calling it for all these kind of events, it's going to be being hit a ton. But definitely useful stuff that you can do. So I think in Ruby 2.0, the trace points, So in Ruby 2.0, the trace points was added, which is an object-oriented version of set trace func. And so it also adds these other events on top of it. So in addition to all the events from before, you also get any block call or return, as well as any time you start or end a new thread. And so this is the same example from before, but using trace points. And so as you can see, we have a trace point class that we can instantiate, and then inside of it, you pass a block with this trace point object, and then basically it has all those same arguments, but they're attached to that object. And then we can go through and then just enable it inside of a block, so it only gets run in that block. And so we can do that same thing, and we see fairly similar output. We don't have the set trace func starting thing this time, but it pretty much corresponds to all the exact same stuff as before. So returning all that information. But one of the nice things about trace points that you can't do with the kernel is that you can actually limit it, as we see here with this trace point new, limit it to specific events. So it only gets called on specific events. It's not getting called for every single one of those events from before. So you can severely limit the amount that, and scope it down to the things you're actually interested in. So Matt Eminetti, actually, when TracePoint came out, wrote this middleware that I just took and turned into a gem to be able to just use for some of the code samples here to try to get some information. So what I wanted to do, or what this middleware does, was it basically goes through and for every single class that gets defined when this call event happens, we store it in this hash and we just count the number of method calls that happen, because I just wanted to start calculating some information of just like what happens inside of a rack app when we're doing a call to kind of compare like how expensive it is to do some of this stuff. So that was kind of the main middleware, and this is just kind of calculating the information there. So here's my very simple rack app that uses this middleware. I'm just calculating the Ruby version that I'm running, and then inside I have the middleware set up and I kind of run that there. So how many methods, so the middleware just calculates the number of classes that are used and methods that are instantiated, or methods that are, unique methods and number of methods that are dispatched. Like, do people have a guess of what the number is for this very simple rack app? 60? Well, the answer is 1. So, like, there's one class that is used, it has a single method, and only dispatches a single method to run this rack call. So it's pretty simple. So then, building off of this, I was like, oh, well, let's see how the most popular micro framework works. So I have essentially the same functionality, but in a Sinatra app. And I did that. Do people have guesses for the numbers here?
60. Yeah.
60? I thought the answer for everything is 42, though. So like, it uses 43 classes for that single GET request, 155 methods, and then 548 methods that are dispatched. And of course, the natural conclusion is, or the natural, if you take this on the path, is like, okay, let's see what happens when you do this with Rails, right? So I have like a very simple Rails controller that just returns the string in the view. Do people have guesses for that? It is not 60.
2,000.
2,000? So there's 361 classes, 1,200 methods that are actually used, and it makes almost 9,000 methods dispatch calls just for a single request. So this goes and shows like the kind of power information you can get from kind of instrumenting your app with trace points and set trace func. Just being able to feed into those different calls and events. So here's an example of the JSON output of that dump. So one of the things you can do that's really neat is, so this shows you inside of this Sinatra base class, these are all the methods that were actually called and how many times they're called. And so one of the things that I just did was just to go through and sort. So in that Sinatra example, ERB compiler buffer, the push method gets called 133 times. So doing all this ERB stuff is actually computationally, or is pretty expensive in the sense that like that is some of the main methods that are being used just to do the templating there. But it's just like interesting stuff that I wouldn't be normally looking at without access to this kind of information. So the next thing I wanted to talk about was object space. So this has been around for a little while, and I think, and so you can do things like, it has count objects, so inside of your Ruby, you can just call count objects and it'll show you the different counts of the various objects you have inside of it. And you can obviously sort that and do what you want with that information. The other thing it provides is this each object method call. So it allows you to literally iterate through the whole object graph. And this is pretty expensive for a real application. And I'll go and show you actual timing information later on of like how expensive it is. But this is a very simple example of like iterating through each of the objects and then basically just counting how many objects there are for each of the different classes and sorting them. So inside of even this simple Ruby program, we're getting like 10,000 strings that are being allocated, right? Or so even like with a bare Ruby program, you're still instantiating a lot of objects here. So in Ruby 1.9, there was a C extension called object space. So if you require objects OBGJ space, you get a bunch of other things that get added onto object space. And one of the main things I wanted to talk about is allocation tracer. So with allocation tracer, you can start to introspect the actual objects themselves. So this is an example of using trace object allocations. And similar to the trace point example, we can, for a single object, you can kind of fetch all that same information here. So there's methods on object space where we pass the object in and we can get all that information. So for the same example, you can see we're doing that and we get the line, the method and the class being instantiated. Obviously we don't have the event calls because this isn't hooking in through the events and it's hooking in just through the objects, but we can kind of see all that information there. But some of the more interesting stuff is I wanted to look at what you can actually do with with the information that you get from object space in Allocation Tracer. I wanted to just build a simple thing that would calculate some of the memory stuff. So I wrote this middleware that basically goes through and does a memory calculation around a single rat call. And then we store all this information inside of this struct. And inside the calculation, we're basically walking through the graph of objects. So at first we wanted to figure out all the objects that already exist before we actually make that block call there, and then go through all the objects again after the block call, and then skip any object that has already existed before, because we only want to count and look at the objects that have been created since that call has been made. So any matching object ID we're going to skip, and then everything else we're going to store into this hash of all this information that we're actually interested in. And then this is just some sorting code to kind of sort the output based off size. So given so with that Sinatra example, when I inserted this middleware in and took the other one out, it took on my computer about 4 seconds. So my computer is kind of old. This is from 2011, but it can kind of go to show that, like, even for that that Sinatra app is very, very simple for that single GET request, and it took a whole 4 seconds to just run it. Whereas, like, you're getting the stuff in milliseconds from before, so it's pretty expensive to actually walk through that graph. And this is the kind of output that you're going to get. So again, we're going to see where in the code that this stuff is being called from, but you can see the method that's actually being called, and inside, like, what the memory size using this mem size call is in bytes. So just going through that simple Sinatra example, again, we're seeing E or B, which isn't too surprising given the information that we found from before. But this is sorted by size. And so this is object counting for Sinatra. And so then I did the same thing for Rails, and for that simple Hello World Rails app, we're seeing almost 11 minutes to just walk through that graph. So, like, super expensive, and obviously not something you'd want to do in production, or I don't think you want people waiting 11 minutes to get a request back. But from Rails, we can see these are the different objects being created that are kind of lying around when you actually make a GET request. So, I mean, it's just, like, interesting to see this kind of information. So as Richard was talking about, Memory Profiler does a lot of this work for you, and it will break it down in much nicer outputs inside tables. And so this is kind of the base work of, like, how a lot of that stuff works inside Memory Profiler, of what it does. It uses object space pretty extensively, but so I'd recommend checking it out for just introspecting your running Ruby applications. So the final thing I wanted to talk about was the Allocation Tracer gem. So this is, like I said before, a gem written by Koichi to kind of help with look at, like, objects being allocated inside Ruby. And like Richard was showing in his talk, like, the more objects you're allocating and how much memory you're taking can significantly impact the performance of your Ruby application. Even if you aren't hitting swap, it's objects that are being created have to get GC'd if they aren't being used later on. And as we all know, GCs will stop the world, so it can be pretty expensive to have to do this pretty often if you're creating a bunch of junk objects. So since it's a gem, you just install it, put it in your gem file, and Koichi actually showed us, Richard and I, like, how to use this gem, and I had this sample algorithm that I kind of wrote, and it goes through and just kind of swaps stuff inside this array. It doesn't really do anything really complicated. Using the Allocation Tracer gem, we can kind of trace, like, what is actually happening here, and to see the number of objects for this very simple use case here. So this is the output that you're going to see, and to kind of break it down, you get the file information, which is similar to all the stuff from before. You get the file name, the line number it's on in that file. You see the total number of objects created in that line, which is very useful information. The number of old objects that are still lying around on that are created on that line, the total age of the objects there, the minimum age of any of the objects, so in this case 0, because they were just created, the maximum age of any of the objects, and the memory size without the R value. And I was actually asking Koichi about this yesterday, but mem size will return kind of the total size of memory being used, but it's not a completely accurate count. And the R value are the class primitive information that you have for each object. So this returns that information, how big it is without that stuff. So if we go back to the output, we see on line 15 that we're allocating 10,004 objects, which kind of makes sense. I mean, we're iterating over 10,000 items, and we're basically mapping that into an array. But we have an extra 4 objects being lying around. And then we also notice that on line 7 that we're instantiating 5,000 objects, which again, if you look at the code, kind of makes sense because we have this pivot point where we're creating this thing that's divided by 2, so half of 10,000 is equal to 5,000, so that kind of makes sense that we're creating those objects there. So one of the nice things about allocation tracer that we found out was that you can actually set up the kind of keys on the left of what it defines. So normally by default just this path and line, but you can also specify type. And when we do that there, we get this output, which is a lot more useful, I think, for kind of digging in. So we had that 10,004 from before, and we can see how that's actually broken down. So we have the 10,000 strings that are being created from the initial array, and then we also have the array object being created as well as some of these other data types. And then we notice that on that line 7 we have 5,000 arrays being created, which doesn't quite make sense for what I was thinking was happening on that line. But this definitely gives us insight into what is happening. So this is that line 7 where the 5,000 arrays are being allocated. And Koichi basically told us that it's because of the way the assignment works when you do this like multi-assign on the left here, and because it is indexing an array here and not just like an individual XY variable, it has to save the value in case you have any side effects from that method call, because indexing is actually just a method call there. So we actually need to create those objects to make sure that if anything if any side effects happen, like we have the original values there. So we can actually optimize this by doing a normal assignment and then kind of doing that assignment ourselves. So this is not as pretty as this, but when we go through and run the code and trace it, we see those 5,000 arrays not being allocated because we're not doing those side effects. So this goes to show how powerful it is to actually be able to introspect using allocation tracer the kind of objects that are being created and what you can actually, like real world use cases of what you can do with this information. So I went through and again wrote rack middleware that basically went through and ran allocation tracer around all the calls inside of rack. So for that single get request, this is the kind of output that you're going to get, so you can kind of dig in and see like the actual allocations happening in your own code. And then this was the same thing for Sumatra. And as you tell, like a lot of this stuff is inside your actual vendor libraries, but if you wanted to scope it to only your code, you can obviously search through that, and this is kind of the output there. So it falls in line pretty regularly with what you would expect. That code's not doing anything really complicated. So in conclusion, there's a lot of tools actually out there. I know like I've been known to complain about the lack of tooling in Ruby, but it's definitely gotten a lot better. And having written this talk and kind of looked and played with this stuff, there's actually a lot of really useful information that you can get from just the core standard library of tools and obviously the allocation tracer gem. And this is stuff that when you're examining things from like New Relic or other agents, that all these like when you're seeing memory growth and other things, like these are definitely tools you can go through and reach to kind of introspect code outside of production to dig in and see the kind of information that you can get and help optimize your application. Thank you.